Welcome to this video on linear first order equations. Let's first take a look at what these equations are and how to identify them. And then our solution approach, so that we know the general method to solving these ODEs. And then an example where we specifically apply the solution approach to solve an ODE. All right, so what is a linear first order equation? The answer is in this box on the screen. And it's any ODE that you can rearrange and manipulate to get it into this form. And what is particularly interesting about this form is that the derivative dy and dt stands on its own. There's no coefficient in front of it. And that the y as well in this equation only has a coefficient that is determined by some function of t. A function of t could include constants as well. So p of t could be equal to 10 if it was 10y. So it also can be numbers and constants, but especially can be functions of t like log t, sine t, t squared plus 1, anything like that. But what it's not is it's not y times y or the derivative times y, it's some function p of t. And on the right hand side, we have it equal to some function q of t. And if you can get into this form, it's a linear first order equation. And the reason why it's useful to be able to put it into this form is that we actually have a general solution approach that we can use to solve this ODE. And if you can correctly identify it and get into this form, you can then follow these steps and solve it using this method. Okay, so let's just look at some examples. These three ODEs, the left and right one are linear first order ODEs and the middle one is not. So just to elaborate on why that is, if you look on this one on the left here, we have y dash standing on its own. We can move t squared y to the left hand side, and then we have equals to t to the 5, and that would make p of t t squared and q of t t to the 5, and it's perfectly in that form, which is great. This one here is not a linear first order ODE because y dash and y are multiplied by each other. To separate that out would break the structural integrity of this form, because you would either have y dash is equal to 1 on y. So now we're not multiplying y by p of t. It's 1 on y multiplied by something. That's not good. Or vice versa if you tried to rearrange it the other way. There's no way you can separate this out to give you this form. And on the right hand side, in this case, p of x is just 0 and q of x is log x. And then we have it in that form. So those are just some quick examples for us. Okay, so what's the general solution approach? I'll walk you through these steps, which if you don't know why it works, won't mean anything, but I'll walk you through them and then I'll explain why it works. Okay, so step 1, write it into this form. Just because you have a linear first order ODE doesn't mean it's already represented in this form. Usually you want to identify that it's linear and then move things around to get it looking like this. Then step 2, you want to find an integrating factor that is I is equal to e to the power of the integral of p of t dt. So that's whatever this function is, you want to integrate it and then construct this integrating factor e to the power of that. Again, I'll explain why this works and it's useful in a moment. Step 3, multiply both sides by the integrating factor and then put it into this form. And then step 4, integrate both sides with respect to t. That will cancel out this derivative and the right hand side is only in terms of t, so that's just standard integration. Then you can rearrange it and solve for y. Okay, so this whole process is dependent upon the fact that we can multiply this linear ODE with this integrating factor I, and then put it into d of dt I times y is equal to I times q. So let's take a look as to why that works and why that's useful. So I've got the derivation here below. If we start by just, considering our linear first order ODE like this, and then we multiply both sides by I of t and expand out the left hand side, we now have I of t dy and dt plus I of t p of t y is equal to I of t q of t. And what we actually want is to have an application of the product rule on this left hand side. If this left hand side is the application of the product rule, then ultimately we can condense it down into d of dt of I times y. And for that to work, we're going to need I of t multiplied by p of t to be equal to the derivative of I. So if we look here, the product rule is that the derivative of u times v is equal to u dash v plus v dash u. And if we look at y as our u, then this obviously is u dash, it's dy and dt. And then this is u, it's y. And then v, we've got I of t, and then we want v dash to be I of t, p of t. And that's exactly why we're constructing our integrating factor like this, so that v dash is going to be equal to this. So we want the derivative di and dt to equal I of t, p of t. And if that is true, then that means that this is indeed an application of the product rule. And so I divided by I of t di on dt is equal to p of t. Integrating both sides with respect to t. And we get this. Okay, if that wasn't clear, let me try that again. We want di and dt to be equal to I of t multiplied by p of t. That's what we want. And if that is true, we can use the product rule here. And then now we want to rearrange and solve for I of t. So this is actually a separable ODE that we can solve to figure out what we want our integrating factor to be. So that's what this next step is dividing both sides by I of t. And then integrating both sides with respect to t. And then that makes this left-hand side a new integral with respect to di. And this right-hand side an integral with respect to t. And then integral of 1 on I is ln absolute value of I. And then if we take the exponential of both sides, we have I is equal to this. And that means that this is a solution and it is a integrating factor. So that's why we choose our integrating factor to be this, so that when we follow our solution approach, we indeed get the application of the product rule here, where d on dt I times y is equal to this mess that we created for the sole purpose of cleaning up the mess into this form. All right, so I find a lot of students find this whole process quite confusing, especially conceptually, and why they do it. But it does work, and at the very least, you should understand how to follow the steps. And perhaps over time, this will become clearer as to why that is actually working the way we want it to work. So yeah, let's take a look at an example and solve it together using this methodology to do so. Okay, so here's a very simple, well, it's actually simple in its representation here, but the answer is not as straightforward. Anyway, we've got dy and dt equal to y plus t. Determine the function y of t. Okay, first of all, is this a linear first order equation? Yes, I mean, I wouldn't put it in this video if it wasn't, but just looking at it, we can rearrange it by putting, well, let's actually do that. We can put dy on dt minus y is equal to t. And then we can identify what actually our functions are. So we want to identify p of t and q of t. Well, here p of t is going to be equal to minus 1. So p of t is equal to minus 1. And then q of t is equal to t. Sorry, excuse my phone, I will silence that. Yep. Okay. And then we've completed step 1. Tick. Step 2, find an integrating factor I is equal e to the power of the integration of p of dt. So I is equal to the integration, is e to the power of the integration of p, which is minus 1 of dt. So that is equal to e to the minus t. Now we're just looking for an integrating factor. Of course, we have our integrating constant to work out all possible solutions to that, but we only need to use one solution so that we can leverage that solution to determine what the ODE actually is. So this is a integrating factor, and it's the one we're going to use, whether integrating constant is 0. Okay, so our integrating factor is equal to e to the power of minus t. Let's now multiply this into this equation here. So I'm going to multiply both sides by I of t, and therefore I'm not changing the fact that they are equal. And that gives me e to the power of minus t dy and dt minus y is equal to the e to the minus t multiplied by t. That's multiplying this by I of t. And then I can expand that out. Yep. And then I will ultimately want to integrate both sides with respect to t, but leverage the fact that this is already a derivative with respect to t. So here we can actually acknowledge that now. d on dt of y e to the minus t is equal to e to the minus t multiplied by t. So why is this the case? If you were to differentiate this, you'd have u dash v plus v dash u. So u being y and v being e to the minus t. U dash is just dy and dt. So we've got u dash v, u v. Okay, I think maybe just to be really clear, I'll just write it out. U is equal to y, u dash is equal to dy on dt, v is equal to the e to the minus t, v dash is equal to minus e to the minus t. Therefore, d on dt of y e to the minus t is equal to u dash v minus v dash u, and that is equal to dy on dt e to the minus t minus e to the minus t, so that's a plus, e to the minus t y. So that is exactly why this is equal to this, just in case it's not clear. And this will work every time if you use your integrating factor and establish it with this method. Okay, back to here. Integrating both sides with respect to t. Gives us this. And for the left-hand side, differentiating this with respect to t and then integrating it with respect to t is cancelling out. And so that is just left with y e to the minus t. And then we have that being equal to e to the minus t dt. Okay, great. So we've actually condensed down our problem a lot now. The only thing we need to do is solve for this integral, and then we can rearrange things to give us y as our function of t. All right, good. So how do we solve this integral? Well, it's actually not straightforward. We need to use integration by parts. But once we do that, we'll be pretty much done. So integration by parts, maybe if you aren't familiar with what that is, I'll give you a quick refresher. Integration by parts, if you have the integral of u v dash, that is equal to uv minus the integral of v u dash dt. So you can think of integration by parts as a tool to try and make this integral solvable, and essentially you swap derivatives from u v dash into v u dash, and you get something outside of it as well. But swapping derivatives here might allow you to make things simpler because you can anti-differentiate v and then differentiate u, and you have a new integral here that could be simpler. And when I'm looking at this one here, which I'm trying to solve, integration by parts is an excellent choice to solve this, because if our u is our t here, then when we differentiate u, we just get 1, and multiplying v by 1 is going to just be v, and that allows us to break down this integral into something solvable. So that is what we're going to do. Okay, so u is going to be t, u dash then is 1, v is e to the minus t, and so, oh wait, v dash is e to the minus t, and so v is going to be minus e to the minus t. That way when you differentiate it down, it gets rid of the negative. Yep, that's good. Okay, so that makes our integral here, integral of e to the minus t, t dt, is equal to uv, so t multiplied by v, which is this one, minus the integral of vu dash, which is e to the minus t times 1 dt. And then that's integrating this with respect to t. That's pretty simple. It's just minus e to the minus t. And then because that's minus of that, overall is plus. No, there's a minus in terms of v here, which makes this back to minus. Okay, 3 minuses, so overall a minus. Okay, and then it'll be appropriate for us to put in our plus c, because this is the last integral that we're looking at, and we want to connect it back up with this one and include that integrating constant. So, okay, using the fact that this integral is equal to this, we have therefore y multiplied by e to the minus t is equal to minus t e to the minus t minus e to the minus t plus c. And c is some real number. And then multiplying the whole thing by e to the t will get this to give me y. And then the right hand side is minus t minus 1 plus c e to the t. And then c is some real number. Okay, and then that's our answer. We now know that the function y is equal to this. And any solution, any c being a real number, will generate a solution for this ODE. And that is actually solving this initial question of determining y of t when the derivative of y with respect to t is equal to the function y itself plus t. So this is the answer. Anything of this form will work. All right, that's the end of this video. I hope you learned how to, 1, identify linear first order ODEs, and 2, solve them. That's everything for today. Thanks for listening.